Morning, y'all. The final exam is posted. It's linked right here. Which is, it's the Thursday of finals, Thursday morning. It's a final exam. And a couple reminders about that. So first reminder is you do not have to take the final exam. It's up to you. I think the final exam is only required if you want an A in the class. And so whatever your contract was, right, you should know whether you are planning to take the final exam or not. I mean, you can still change your mind about that. That's fine, but is that gonna be your question?
Related to that, but
Okay.
when are caddis problems due you if you don't?
Caddis problem. So yeah, that's like this. I'll get to that in just a second. Good question. So the final exam, it'll be very similar to the other exams. A little bit different though. It is comprehensive, so it covers everything from the semester, except not what we're going to do this week. It's not on the final exam. But there is, I think there are 5 questions on the final exam, and you can choose any 4 that you want to do. So there's a little bit of choice. The other difference with the final exam is because there's no opportunity to revise it. So for this exam, I am happy to give feedback on solutions ahead of time. I'm not going to give you hints. But if you could be like working on, all right, you're like, I think I've got a good solution to number 3. You can come to office hours or send it to me, like write it down and send it to me, whatever, and just say, what do you think? Here's my idea. And I might say, that sounds great. Or I might say, well, I think you're on the right track, but that thing you said, like you haven't yet shown this missing part, right? Or I don't think what you just said is true because here's a counterexample or whatever, right? I'll give you some feedback. So ideally, if you want to take advantage of that, you should be able to go into the final exam being pretty confident that you're going to do well because you're like, I've kind of checked all these with Dr. Yorgi and he said they're good. So that's the intention there. And then when things are due, so I sent an email about this, but just be there. So anything, caddis problems, old problem sets, old exam retakes. So the Friday of finals week is the last day that I will hold office hours and the last day that I will give feedback on stuff that you turn in. So if you turn in anything by Friday, I'll send it back to you with comments or whatever, and you can revise it. You can continue to turn in stuff up until 5 p.m. on Tuesday the 16th, but basically anything between Friday and Tuesday, or like anything from Saturday to Tuesday, you can send it to me and I will grade it, but I'm not going to like send you feedback. You won't really be able to revise it. I mean, I guess you could still try if you find out that you didn't get credit for it, you could just try submitting again and hope, but anyway. Does that make sense? Any questions about that? Cool. Yeah.
Still the offer caddis problems instead of a final test.
Yeah, of course.
And when would those be due to do that?
Oh, good question. No, we'll just say it's the same schedule as same deadline as anything else. So yeah, if you are intending to get an A and you want to do like one caddis problem from each group instead of the final exam, yeah, of course, nothing has changed in the syllabus, but yeah, you can turn those in. They in particular, they're not due by the time of the final exam. Like you could do those, anytime. And I guess for those, it doesn't like this Friday versus Tuesday doesn't really matter because you already know if you got them right. So as long as you submit them by end of the day on Tuesday, that would count. If I were you, I would try to do it earlier than that, but just to not cut it that close. All right. So this week, this is kind of bonus in a sense because this is not even going to be on the final exam, but it's a pretty cool topic, and it's relevant, and you might hear people talking about this. And I think it's interesting to. You can find lots of sort of treatments of this from a sort of pop pop culture or the pop science point of view, but I think it's interesting, given what we've talked about so far this semester, it's interesting to look at it from a kind of algorithmic point of view. And if you take theory of computation in the spring, you're going to see this again, but from a different perspective. All right. So what I want to start with is everything that we've done this semester so far, right, has typically been, we're like, all right, here's a problem that we're interested in. Here's a brute force solution. Gosh, that's really terrible. And then we think hard, and or I just tell you about some clever thing that someone came up with in the past, and we're like, oh, cool, you can actually solve it a lot faster than that brute force. Neat. And you would be forgiven at this point for thinking that, like, that's always going to be the case. But there's definitely some big selection bias going on. Like, I've been showing you things that we do know good ways to solve them, right? I haven't told you about other things. But it turns out, unfortunately, there are a bunch of problems that it turns out there are a bunch of problems that not only do we not know of a better algorithm than brute force, but we have some pretty good evidence that there cannot exist better algorithms than brute force. And some of these are even problems that people really care about. It just turns out that it's, as far as we know, it's not possible to solve them better, more efficiently than brute force. So let me tell you about, I'm going to start by just telling you about a couple different such problems. So the first one has to do with something called independent sets. So let me just say hard question mark problems. So first one, an independent set in let's say an undirected graph, G, a set of vertices instead of edges, is a subset of vertices. We'll call it S, is a subset of V, such that no two vertices in S are adjacent. Between adjacent and connected, right? So adjacent means they literally have an edge going between them, right? Connected means there could be some path, right? We're not talking about that. We're just saying you have some vertices, but there's any two vertices in your set, there's like do not have an edge directly between them, right? And let's do an example. I have my little example here. Draw this. 6, 7. And I'm going to make some edges here. And make some edges here. Okay, so here's an example. So someone give me an example of an independent set in this graph. What do you think? There you go. 1, 6, 4, 5. Okay. What do y'all think? I guess before I write it down, we should check, right? So Nico's saying 1, 6, 4, 5. So what do y'all think? Does that count as an independent set? Yeah, you look at this set of vertices, right? There's any two blue vertices, there's not an edge directly between them. So that counts. Okay. Someone give me another one. 3, 4, 5. What do y'all think? Does that count? So 3, 4, 5. Does that work? Yep. Okay. So another one. 2 and 6. What do y'all think? Does that count? So 2 and 6. Is that an independent set? Yep, I agree. Okay. Let's do 2 more. 4, just 4 by itself. Does that count? What do y'all think? It is a subset of vertices. And yep, there's no 2 vertices in that set that have an edge between them. So yes, I agree that counts. All right, what's one more? 1, 4, 6. Yes, I agree that counts too. Okay. How about the empty set? No one said that. Would the empty set count? We vote?
No.
Okay, you think no? Why not? Doesn't have any vertices, so the definition doesn't say it has to contain vertices. I mean, I guess it depends how you, yeah. Like the empty set is a subset of set of vertices. And yeah, if I have no vertices, then it's true that no 2 vertices in S are adjacent. So yeah, empty set actually counts. Not a very exciting one, but okay. So given this concept of an independent set, what are some interesting questions that you might add, like given a certain graph? What are some interesting questions you might have about independent sets? Yeah. Okay, so like a largest one might be an interesting question. Yeah, so total number of independent sets. Other interesting questions you can think of? What about smallest independent set? Is that interesting? See some shaking heads. Why not? Yeah, empty set is always an independent set. So yeah, that's not interesting. But largest, right? Why is largest interesting? Well, because it's like the more vertices you add, the more difficult it is to find vertices that, such that none of them are adjacent to any others. So it seems like it's really easy to find small ones, but it gets harder to find bigger ones. And so it's interesting to ask what's the largest. By the way, do we think that 1645 is a largest independent set in here? Seems like probably, and it turns out, yes, it is, but not necessarily, it's not obvious how you would know that for sure. I mean, in this graph is small enough that you can kind of look at it, you could probably reason some things out and be convinced that, yeah, that's the biggest one. But okay. So I want to talk about this question. This question, it turns out people do care about. And actually, I'm going to come back to that in a second. Because we can kind of talk about these both. What would be like a brute force algorithm for, let's just focus on this question. So if I want to find a largest independent set, what would be a sort of a brute force algorithm for doing that?
Every single possible set.
Yep. Okay, I agree. So list every subset and check if each is independent. And then just kind of keep track of the biggest one that we see along the way, right? How long would that take? No. I don't think so. I don't think it's quite that bad. Because factorial would usually come up when you care about when you're listing like every possible order of something, right? Because it's like, well, I have n things I can put first, and then n-1 things I can put second, and so on. We're just looking at sets. We don't care about what order they're in. So how many possible subsets are there? Yeah, 2 to the n, or in this case, if it's like 2 to the v, if v is the number of vertices. And then, how long would it take to check if a subset is independent? Naively, I guess it, maybe something like v squared, because you just kind of have to like check every possible pair of vertices and see if there's an edge between them, right? So this is something like, O of 2 to the v times v squared, which is pretty bad. I would not want to be using that algorithm for anything. Like, if v is up to about maybe say 15, you could do it. If v starts to get much larger than that, it's like, forget it. It's going to take like years to run this other, or decades, or millennia. Here's the crazy thing. We don't fundamentally know of a better algorithm than this. Now, you can do a little bit better. So probably, I haven't thought about this carefully. Probably you can do some clever things. Because like if you're like, well, if I list every subset, and then for each subset, I check which things are connected. Like it seems like you're redoing a lot of work. Every time you do that check, it seems like you're kind of redoing a lot of work. And probably you could be clever and maybe get rid of this and have it be only O of 2 to the v. So you're kind of like keeping track of some checks you've done. And so like each subset, you only have to check a little bit of extra stuff or something in a way that it would be only O of 2 to the v. And maybe, and I've seen other similar things, like you might be able to do some really clever things to cut it down to like O of 2 to the v over 2 or something like that. But the point is, fundamentally, every algorithm we know of to solve this like is exponent, has a v in the exponent, right? It's like 2 to the something that involves v. It is not some polynomial, right? So fundamentally, we don't know better algorithms. And then going back to this question, like the total number of independent sets, I think I did a little bit of searching about this, and as far as I can tell, the state of the art is there's kind of some clever algorithms to go through and list all of them by just kind of like searching, and it's essentially the same algorithm, right? But instead of keeping track of the biggest, you just like keep track of a counter. But fundamentally, you're just kind of like listing all the sets and checking which ones are independent, but maybe in some slightly cleverer ways, right? But okay. We mentioned a couple things before I tell you another example. So one thing is there's a very related problem called the vertex cover problem. Oh, sorry. No, even before I say that, I forgot one other thing I wanted to say. I started by just presenting this abstractly, but it's not hard to come up with scenarios where people might care about this problem practically, right? So think of these, like one natural way to think of this is if you think of an edge as like a conflict, right? Be like, okay, we have a bunch of things and we draw an edge between two things if they conflict somehow, right? And then an independent set is a set of things such that none of the things conflict with each other, right? So think about like, you have a bunch of people, but some people like have conflicts of interest, and you don't want to put them both on your committee, or you have a bunch of tasks you can do, except for like some tasks might require the same resources, and so you can't do those tasks at the same time, right? Like maybe task 1 and 2 both require the use of your ruler, and you only have one ruler, and so you can only do one of those tasks. And then you're like, all right, I want to like do as many tasks as I can all at once, but we can't schedule multiple tasks that require the same thing that conflict, right? Another related problem is called the vertex cover problem, which says you want to find a set of vertices such that every edge is touching at least one of your chosen vertices. Sometimes people phrase this as like the museum guard problem. So if you think of the edges as hallways and the vertices are like, guard stations, it's like, and in that case, it turns out it's interesting to find the smallest. So what's the fewest number of guards you can hire such that every hallway is watched by at least one guard? And it turns out that anytime you have an independent set, all the other vertices are a vertex cover and vice versa. And so in some sense, these two problems are kind of the same problem because, let me see if I can convince you that really quickly. So here's 1645 was an independent set that we found, right? And if we look at the other vertices, 327, that is a vertex cover. And so if you look at every single edge, at least one endpoint of every edge is touching one of those pink vertices. Why is that? Well, because if I can never have an edge that goes between two blue vertices, that means every edge has to touch a purple vertex because it can't touch both it can't have both ends both on blue vertices. Anyway, so those are kind of the same. It's the same problem, just like kind of from a flip perspective. But any algorithm that you had to solve one, you could use to solve the other, vice versa. Okay. Let me show you another example. And this is called satisfiability, or people abbreviate it as SAT. And I'm going to try to introduce this quickly, but so here's how it works. So a term is either a variable or the negation of a variable. So, for example, I might have a variable like x1, or x3, or I might have like not x5 to be a term. And people also often write this as like x5 with a bar over it. Doesn't really matter what notation you use. And it doesn't really matter what you name your variables either. You just got some, either variable or not a variable. Okay, that's a term. And then a clause is one or more terms combined with or. So, for example, x1 or not x3 or x4, or just x2 by itself is a clause, right? Or it could be like x1 or x2 or x3 or x5 or not x7 or x10. I don't know, right? These are all examples of clauses, okay? And then a truth assignment is just a way of assigning each variable to be true or false. So a truth assignment assigns true or false to each variable. So for example, if I have three variables, x1, x2, and x3, maybe I might say, well, x1 is true, x2 is false, and x3 is true, or something like that. And a truth assignment satisfies a clause, satisfies a clause if it makes the clause true. So for example, the above satisfies, let's say, x, not x2 or, no, let's say x2 or x1 or not x3. So if we look at this truth assignment here, say, all right, x2 is false, so this is false, x1 is true, and then this is not x3. So if x3 is true, that would make this false. So this would be false or true or false, but that's true. As long as there's one true somewhere, the whole thing's going to be true. Right, but not if I said like x2 or not x3 or not x1. Right, this truth assignment up here does not satisfy this clause because it makes all those false. So the whole thing would be false. That make sense? Okay. And then finally, so far this is not very interesting because you just have ors everywhere. We can say a truth assignment satisfies a collection of clauses if it satisfies all of them at the same time. In other words, we have a bunch of clauses. Each clause has a bunch of ors, and then we kind of imagine anding all of those clauses together. So it's kind of like it's as if we have like some clause and the next clause and Okay, so again, let's do example x1 or not x2. X not x1 or not x3, x2 or not x3. So I have a collection of 3 clauses here. Someone tell me, is it possible to satisfy, can you come up with a truth assignment that satisfies those clauses? In other words, we need to pick values for x1, x2, and x3 that make all 3 of those clauses true.
True, false.
So you want x1 to be true, x2 to be true, and x3 to be false. Is that what you're saying? Okay. Let's check. So x1 or x1 or not x2. So that would be true or false. Right? X2 is true, so not x2 is false. Not x2 is false. So that would be true. What about this one? Not x1 is false, but not x3 is true. So that would make this true. And this third one, x2 is true, so that would be true. Also, not x3 is also true. So, okay, cool. I agree. So satisfies the above clauses. As another example, let's have the clauses x1, x3 or not x1, and not x1 or not x3. Can someone give me a truth assignment that satisfies those clauses? See some shaking heads. So let's think about it, right? The first clause is just x1. And so if that's going to be satisfied, x1 has to be true. No, we have no choice in the matter. So if x1 is true, then look at that second clause. The second clause says x3 or not x1. Well, we already know that x1 has to be true, so not x1 is going to be false. So in order for that clause to be satisfied, we have to make x3 true. So now we've decided that x1 and x3 both have to be true, but now the last one says not x1 or not x3. Those are both false. So there's no way to do it. So we say this is not satisfiable, right? I.e., no truth assignment satisfies it. Okay. So here's the question then, and this is called SAT, right? So given a collection of clauses, right, C1 through CK over the variables, if I have variables like x1 through xn, are the clauses satisfiable? And people really, really care about this question practically. It's not just an academic thing. It's not too hard to imagine situations where, you have some kind of system of constraints and you can encode them somehow in terms of, well, this has to be true or this or this or that, whatever. Less obviously, like what if you have, what if you have something that involves numbers? Like that's not just like Booleans, but it turns out, well, if you can encode the numbers as a bunch of bits, right? And we know that you can make circuits out of like Boolean logic that will do things like add numbers. And so it is possible to express something like x plus y equals z by thinking of x and y and z as a collection of bits and then writing down some Boolean logic things that mean that this plus this equals this. And you wouldn't want to do it by hand, right? But it's not hard to write a computer program to like automatically, you can write down things in some higher level language and then it translates it into like a ton of low level Boolean things, right? And then if you had an algorithm that could solve this, there's a whole bunch of things that you can translate into that language and then have it solve it. So a brute force solution is basically try every truth assignment, right? How many possible truth assignments are there? Well, if I have n variables, each one could either be true or false. So there's 2 to the n. Right? So this is something like, of 2 to the n, times something. I mean, I'm just going to say it's like big omega of 2 to the n. Because like we have to factor in how much time it takes to actually, once you have a truth assignment, you got to plug it in to all the variables and sort of figure out if it's true or false. But But again, we do not know of an algorithm that is fundamentally better than this. Now, there's a little bit of good news, which is that there do exist, I mean, people have made programs to solve this problem, and they do all sorts of clever things to avoid, they kind of learn as much as they possibly can and sort of pick things to try very effectively. So they're not just like randomly trying every possible thing. And in practice, on problems, on real world problems that people want to solve, they do pretty well. And so there are programs that even for hundreds or thousands of variables, they can actually sometimes work efficiently and solve it. But even those programs, fundamentally, there's always going to be some inputs for which they will take 2 to the n time. We don't know of a way to like fundamentally do it faster than that. Okay, and here's a variant. The same question, but where all the clauses have exactly 3 terms. This is called 3-sat. Right, and this is definitely it's a more restricted version, and you could imagine that maybe this is easier because we don't have to deal with like giant clauses with 17 terms. Maybe if we know that every clause has exactly 3 terms, maybe that helps somehow, gives us a little more to work with. Turns out that is not true. And how do we know that? Well, we know that because it turns out that if you could solve 3-sat, if you had like, let's say you had a little magic box that someone handed you that could solve 3-sat, then you could use that to solve sat. In other words, if someone hands you a bunch of clauses with any number of variables, you can always translate it into a set of clauses with exactly 3 variables per clause. It might be more clauses, but not too many more, such that the answer to that is the same as the answer to the original question. And so you could like take your clauses, translate it into a bunch of clauses with exactly 3 and put it into your magic box, and out comes the answer. And 2-sat, where every clause has exactly 2 terms, it turns out you can solve that in linear time using depth first search. I won't tell you how that works. It's very clever, but so 3-sat in some sense like the smallest version that's hard. 2-sat becomes easy. But this idea of like using a solution to one problem to solve another problem, this is a really fundamental idea. And that's what I'm going to spend the rest of the time talking about that. And we've already seen this before, but we didn't call it anything special. But this is a fundamental tool that we can use to like compare different problems. So basically, how do we know if one problem is like harder than another problem? That's the so here's the idea. Let's say, right, I have a little magic box or a black, we can call it a black box. The point is, I don't necessarily have to know what it does on the inside. I'm just saying, let's say we have a little box that can solve problem B. And so I can give it, solves problem. There's some kind of input, and then it does some magic stuff, and then out comes a correct output for that problem. Okay? So if I had that, then there's many situations where you want to think about kind of using it to solve some other problem. And you might do it like this. Right? So I want to solve problem A. And so, right, some input for problem A comes in. I might have to transform that input somehow. So I'm going to write like f of x. So I do something to transform it into an appropriate input for problem B. Problem B outputs some answer, right? Maybe I have to transform the answer as well. And then out comes an answer. And as long as we can do this in a way that will correctly solve problem A, right? So where have we seen this? So one, I think we've seen it multiple places, but one place for sure we've seen it is when we talk about max flow. For example, remember we talked about the bipartite matching problem? And so, so A was bipartite matching. And so the input would be a bipartite graph, right? Some kind of bipartite graph. And then the first thing we do is we take that and we transform it into a flow network, right? So we we have our bipartite graph, and we added like some source and target nodes, right? And that was then, and we added some capacities, whatever, right? And then we said, all right, we now have this algorithm that can solve max flow. So we'll now give our flow network into there. And out came some answer which said, oh, here's the max flow. And then we had to look at that and say, okay, which edges had some flow on them? And then we kind of pull those out, and that's our answer to bipartite matching problem, right? So we reduced the problem of bipartite matching to the problem of max flow. Another example is what I just claimed, that we can do this with sat and 3-sat. That in this case, A would be sat and B would be 3-sat. I claimed, but didn't prove to you, that if you had a way to solve 3-sat, you could kind of use that to solve sat. So if A can be solved in this way using I'll say a black box that solves B, we say A is reducible to B. I didn't spell reducible right. Reducible to B. And we write, and this is really terrible notation. We literally use a less than or equal sign. I can never, this is standard notation, and so that's what I'm telling you, but I can never keep straight which way the less than or equal to goes, so don't worry about it. In some sense, it's kind of indicating that like B is harder than A, because if we can solve B, then we can use it to solve A. But anyway, that doesn't matter. So for example, right, I just claimed that like, so bipartite matching is reducible to max flow, right? And then sat is reducible to 3-sat, I claimed. And then I'm going to make another claim that seems even crazier, perhaps, which is, let me make sure I get the right way around. Three-sat is reducible to independent set. So this problem I told you about originally, it's like, okay, we have a graph and we're trying to find like a big independent set. And then this problem about like we've got some clauses with variables and not whatever, which seem like they don't have anything to do with each other. But I claim that if you can solve the independent set problem, well, actually a slight variant that I didn't mention, but specifically the problem of if you're given a graph and a number, it's like, is there an independent set of this size or bigger? So it's basically turning it into a yes/no version. I'll talk about that more next time. But so if someone hands you, if you have a magic box that can solve independent set, and someone hands you like, okay, here's a bunch of clauses with variables and, you know, not whatever, and they all have exactly 3 variables per clause, somehow you can take those clauses and build an appropriate graph such that the answer to whether there's an independent set of a certain size is the same as the answer to is it possible to satisfy these clauses, which seems crazy. It doesn't seem like they have anything to do with each other. Like, how would you make a graph that has anything to do with this? But it is possible, and I will prove that to you on Wednesday. It's a nifty little proof. And once you see it, you're like, oh, that makes sense. I see it, but it doesn't seem like there would be a way to do it. Do you have a question, Jay?
It seems like when you say A is reducible to B, would that also mean B is reducible to A? It seems like they're.
Good question. Not necessarily. You can imagine that like B is much, much harder than A, and it's kind of like having a solver for B is like really overkill. So as an example, like okay, how about this? Like you can, let's say you have a solver for max flow, right? And you want to know, and really what your problem A is this vertex connected to this vertex? And so you just set up a flow network where like the source is that vertex and the target is that other vertex, and then you see if the max flow is 0 or not. And if the max flow is 0, then they're not connected. And if the max flow is bigger than 0, then they are connected. Right? But that's really overkill. And it definitely doesn't work the other way around. Like if I want to solve max flow and all I have is a magic box that tells me whether 2 vertices are connected, I'm not going to be able to do that. I mean, intuitively, I can't prove that to you right now. Does that make sense? Now, in this case, like sat and 3-sat, it goes both ways, actually. In all these examples, these examples, it does go both ways, but not in general. Yeah, no, and they are kind of equivalent in some sense, but yeah, not in general. All right, see you all on Wednesday.